My name's Tom Dick. I'm a math advisor for Texas Instruments, and this short video is part of the TI-Focus AP Calculus series, where we'll be using TI-Nspire to look at particle motion in a plane, using BC question 2 from 2022 as an example. In this problem, we're given a particle moving along a curve with position x of t, y of t at time t greater than 0, but we're given the derivatives of those two position functions. dx dt is square root of 1 plus t squared, and dy dt is natural log of 2 plus t squared. We're also given a position at time t equal 4 at 1, 5. Now, right off the bat here, we're going to go ahead and take that given information and define these as our components of our velocity function. So I'm defining vx of t to be the square root of 1 plus t squared quantity. And similarly, we're going to define vy of t as the natural log of the quantity 2 plus t squared. So now we've stored away the two components of our velocity vector. Now we can proceed and dive into this problem. Let's go on to part A. Part A, we're asked to find the slope of the line tangent to the path of the particle at time t equal 4. Now that would be dy dx, but since we're given dy dt and dx dt, we're going to use, in a sense, a form of the chain rule. So I'm going to take the y component of the velocity, dy, evaluate at 4, and divide by the x component of velocity at 4. And there's our slope. Now here, because I'm on a computer algebra system machine, it's actually giving me the exact value using natural logs and square roots. If you want a decimal value, a way you can trigger that is just by making any number into a decimal in your input. I actually made them both 4-point, but either one of them would have done the job here. And so we get a result of 0.701018 in decimal form. Okay, let's move on to part B now. Here we're asked to find the speed and the acceleration vector of the particle at time t equal 4. Let's start out with the speed. We're actually going to take some time and define a general speed function. So our speed function, let's call it s for speed. So we'll define s of t, and that's going to be the magnitude of the velocity vector. So we're going to take the square root of the sum of squares of the components of that vector. So it'll be vx of t squared plus vy of t squared, that quantity square root, and there's our speed function. Now with that defined, we can just evaluate s of 4. So I'm going to pull up a math box and evaluate s of 4, and we see, oh, again, because we're on a computer algebra system, we've got it in an exact form. I'm going to add a decimal point in my input, and now we get the decimal form of the answer. So our speed is 5.0353. Similarly, let's define for acceleration vector, its two components. So we're going to define ax of t. Well, that'll be the derivative of the velocity component at x. So we'll pull up the derivative from our calculations menu, differentiate with respect to t, dx of t, and that will define our x component of our acceleration vector. Now we just want to follow suit, do the same for the y component of acceleration. So I'll get a math box, defined ay of t, and that's going to be equal to the derivative of the y component of the velocity. So again, I'll go to calculations, to calculus, and find derivative with respect to t, and then we'll differentiate dy of t. Now once we have defined the x and y components of our acceleration, we can evaluate those at 4. And I'll learn a lesson here. I'm just going to go ahead and do decimal forms here. So when I pull up a math box and evaluate ax of 4, I'll make sure I put a decimal point in there. All right, there's that x component of acceleration. And now let's get the y component of acceleration. So another math box. We'll evaluate ay, and again I'll make it 4-point. And there's our two components of our acceleration vector. In part C, we're asked to find the y-coordinate at time t equals 6. Now, in the beginning, we were told at time t equals 4, the arc particle is at the point 1, 5. So we know the y-coordinate was 5 at time t equals 4. So let's start out with that. We're going to put in a math box, and we'll put the position 5. And we know that's where we were at time t equals 4. So let's add on an integral that will represent the change in the y-coordinate between time t equals 4 and time t equals 6. So I'm pulling up an integral, and we'll integrate from 4 to 6 the y component of our velocity function. Integrate that with respect to t. And we see that we end up with a final y-coordinate position at time t equals 6 of 11.5705. Finally, moving on to part D, we're wanting to find the total distance the particle travels along the curve from time t equals 4 to time t equals 6. That's simply going to be an integral of the speed over that time interval. And remember, we've already defined a speed function. So let me go ahead and pull up an integral in the math box. We'll integrate from 4 to 6. And I'll put decimals on those to make sure we get a numeric answer. We'll integrate s of t dt. And this should give us the total distance the particle travels during that time. And there we go. Well, that completes our discussion of some fairly standard topics in particle motion in the plane. For more resources like these, please see education.ti.nspire.com.